in the spirit of understanding that we are both data generators and data consumers, I just put this little graphic over here from my lab. We do work on all of this planning and collecting, documenting, analyzing, but when we go to these genome browsers, we're also doing the discovery, combining, reanalyzing, and looking into new results, and it's in that spirit that we want to share a little bit more about these other browsers. So Sammy talked about the Ensemble browser, and I'm going to tell you a little bit about the JBrowse. JBrowse does not exist as a database. It's not something like the NCBI database or the Ensemble database. It's actually a standalone browser that you can go and download from their repositories, and you can load your own data in order to display it in here. This usually happens on a server, but there are some preliminary work on having it on a desktop version. So it is less common that you would just go and click it, but somebody in your team, a systems administrator, would do this for you and then would reveal this information. So we actually have a hypothetically working instance. I tried to use it last night and I couldn't, but I think it's because of the latency of the internet. I saw it when I was still in the United States, but so we have an instance of JBrowse that works on a cloud machine from Amazon. It's an AWS EC2 machine, and it's located in Virginia, the actual physical machine. So I don't think that there's a mirror close to us, and I couldn't access it last night. But it's there, and I'll show you a little bit. So I couldn't actually get screenshots of that instance, but it will look exactly like this. So instead of looking at data that says you'll probably look at data that says honey or something like that. But it is the same. So this is what the general browser looks like, and this is what the window that you will encounter when you look at JBrowse, just the browser. On the left, this is a massive collection of data that includes gene models, includes aligned RNA-seq reads, hunting's. I'm sorry that it's so difficult to see. You don't need to read what all of these are, but just an example of a genome that had a lot of data available. What you see over here then is the list, and over here on the right, the area where you display all of the genes that you have uploaded. You have a lot of different functionality when you are just looking at the browser without having logged in. So publicly available are different functions that allow you to open a sequence file. That is, for instance, you have done some sequencing of your own, and you know that you have now the coordinates to align these sequences to the reference genome. So you can just go on your desktop, even though this isn't your instance, and upload it so that you can visualize it. You're just sequencing for something and not ready to share that information just yet. You're just inspecting your work, your preliminary work. You can do that here. And then earlier you were asking me what the different colors meant. In this case, what we have done is that we have colored the different exons by the coding sequence frame. So we were reading a gene model, again in this case where the 5' end is on the left, the box, and the 3' is on this side, and we're reading in the direction of transcription from left to right, and this just means that the coding sequence frame for each of these 3 exons is different, and these two have the same as the one before. Remember that the coding sequence frame will not shift, the phases will shift between exons. We can learn a lot more of those details of the fascinating world of transcripts when we do our workshop. And here I'm just showing you that you have different functionality to zoom in and zoom out and just navigate and explore the genome and some information about it. Once you log into our instance that is available from the cloud, you will actually be able to see a plugin. So on top of this genome browser lives a little piece of code that displays an additional window. So before, you could only see the white display, which we call the evidence panel. Once you log in, you're able to see a inconspicuously yellow part here. Usually it's brighter, but this started just playing tricks with my eyes, I suppose. So that area is called the user-created annotations area. This is where you are going to be working. Some of you are looking at this and go, oh yeah, I remember this before. So the browser now has shifted, the tracks are on the right, and the area where you work is here on the left. You have the ability to change it to a black background or a clear background, depending on how you like to work. I'm not going to explain all of the details of the functions, but rather just give you a orientation of what the window looks like. And so down here, you have evidence tracks. In this case, for instance, all of these on the top are genes that have been dragged into the user-created annotations area. That means these were the predicted genes, and these over here are the ones that are modifying. And so the difference, as you can see, for instance, this gene here, this model, has a yellow box here, but that box has turned light blue. It's just because I decided when I was configuring this that the gene models would have the UTRs look yellow when they are sitting down on the evidence tracks, and they will look light blue once they are actual annotations that I'm modifying. So they contain the same information, but they are two different entities, because this entity becomes the one that I'm modifying, and it will be ultimately the new corrected gene model that I am going to work with. And then down here, in this case, these are RNA-seq reads that have been aligned in that portion of the genome. And here, happily, these RNA-seq reads coincide with the stasis of the exons. The dark part of those RNA-seq reads are the actual portions that are being transcribed. The clear part of the RNA-seq reads are the gaps. Those RNA-seq reads are transcripts, and this is a genome, so not everything that is in the genome is being transcribed. So those are the gaps in between transcription. We have different functionality in here. You can upload your own sequences, as I was telling you earlier. You can color by CDA strings, as just told you. You can actually interrogate this browser with your own sequences in order to identify the region of interest that you're looking for. You can zoom in and out like I was telling you, and then you have a whole different set of functionality on the actual user-created annotation area. This is not, I'm sorry, that is so blurry. I don't know if it's blurry for you too, but it's very blurry to me, so it's not very visible. So I'll just tell you, these slides are available for all of us to go through later. But what it tells you here is that if you right-click on a gene that you are annotating, you have a whole lot of functionality that you're able to perform with them. You can get the sequence, you can delete a portion of one of the exons, you can merge two exons, you can actually use I'll show you a little example of using the experimental data that is supporting the gene that you're inspecting, and use those transcripts to actually extend or reduce the length of your exon so that you can annotate an untranslated region that is supported by the experimental data. You can have 9 different types of annotations, not just genes, but you can actually annotate pseudogenes, RNAs, a repeat region, a transposable element, and we're actually working on creating additional data tracks for the Manakin data that tells us where the gaps in the assembly are and marks them clearly with a black box, and as well tells us what the repetitive areas are on the genome so that it will be clear and easier for us to identify by just looking into this. I really wish we had better connectivity so that I could show you what the big genome looks like right now, but we can imagine that this is that fabulous. In this case, I'm simply giving an example of how I can use, this is again an RNA-seq read down here. This is the part that's being transcribed, and this is just a simulation of how this transcribed part connects to the other part of the read on the other side of that intro, right? You do remember, if it's not being transcribed, then it's not going to show up. So these data actually tell me that this gene model needs to be modified. A little flag here tells me that there is a non-canonical splice site. And if you remember, the transcription machinery walks through the genome and finds those regions, identifies that it's necessary to chop it in there, and then the exon splice, right? But sometimes well, for several different reasons, in this case, the fact that in arthropods there are a lot of non-canonical splice sites, they could identify one here for that reason. In this case, actually, the transcription evidence shows us that the canonical splice site should be up here instead of down here. So if you see this red line that I am showing here that I've kind of highlighted with the laser. It shows us that the actual gene model should follow what the majority of the reads of RNA are telling us, and it is that the splice site is located in this base pair, so that the TGAT is here. That you can, once you're done with all of this information, you can download the data that you're working on as GFF3, or you can download it as FASTA files. Claudia and I were talking about just earlier about what happens when you're done with all of this work and how do you make it available again to the community. So that's a long and complicated question, but basically we have to make sure, this is in the spirit of, reminding us that we have to make sure that all of the data that we generate is placed back to the community, not just lost in a supplementary material section of a document, but instead that one, we make it available through our browser. Two, we provide it back to the providers of databases, so the NCBI and Ensemble. If we're making certain modifications, they're not going to be so welcoming of this data, but they would put it at the very least as alternate forms of that particular gene. And so it is up to us to make sure that the knowledge and time that we're investing in improving these gene models gets back to the community, not only benefits us, but also our collaborators. This is just to say that when we do this, we can do this in a collaborative manner, asynchronously. That means not all of us have to be sitting down at the computer at the same time for this to work. However, if I'm sitting down in California and Morgan is over in Pittsburgh, then I'm going to be able to see all the changes that she's making, and she's going to be able to see the changes that I'm making if we choose to do that in the same gene model. So if we have a discussion about what exactly should be happening, this is actually possible with the system that we have put in place for you. These are details for a lot of details more for what the browser is doing. Again, the data tracks that I was showing you before are going to show up here in are going to show up here on the right, and so you just click or unclick, just follow the little tick in order to display them on the left. And a list of all of the annotations that your collaborators have done is also going to be available for you to review or not. A lot of people get worried that when you're doing the curation process, others can see what you're doing. And I encourage us to think about this in the spirit of collaboration and not destruction. The majority, I have trained over 1,000 people in the use of Apollo over the past 5 years. And I have never seen a group, never, of all 1,000 people that has just said, oh, we cannot come to an agreement, I'm gonna delete their genes, so help me, right? Like, everybody comes to a conversation, and I'm hoping that will be the case here. Should you be finding yourself in the position of editing the same gene at the same time, or thinking about editing that gene? On the left, a list of more tracks. This is more information, in this case, an RNA-seq track. So every time you click one of these, it's going to toggle on the data panels on the left. And then the possibility for you to search. There are like boxes that allow you to search by typing into the box. They say that you know exactly which scaffold or which chromosome you're looking for, or linking group in this case. Instead of a chromosome, and then you can orientate yourself that way instead of having to work for it. These are just more panels that show us the list of organisms, so you can have more than one organism in a single instance, which is very useful for us. It's going to be very useful for us if I am working with 2 different species of manakins. I don't have to log out and go back in, but I just click on one or the other species. We don't yet have the ability of having syntenic tracks where you can see both of the assemblies, but we are working on doing alignments of the gene models of one species to be aligned against the other, the reference one. So the Manakin data to be aligned against the picture, so that you can look at what those gene predictions look like, and hopefully from all of the other genomes. That's going to be the most important set of alignments for us to have, in addition to all of the RNA-seq data. And then for those of you who are more sysadmin oriented, and for those of us who are going to be playing the function of gatekeepers, we also have the ability to review what people are doing with their annotations. And we also have the ability to review what the sequences are and to modify the information that we make available to you during the creation process. There's a lot more information in the weeds that I could be sharing, but I think I am going to save that for when we're actually sitting down with our computers and looking at the instance so that it actually sticks a bit more. So this is what that, just the close-up of what that gene browser looked like once we're logged in. The information on the left, the gene models that have been predicted, in this case by, I think this was a combination of Maker, and then this one was from NCBI. Those two gene models that are here actually are in agreement, but these ones are not. Again, for instance, no one did not predict the UTRs, but our combination of Maker and Exonerate, which includes our NASIC data, did predict those. And then over here on the right, the list of annotations. Okay, that's all about JBrowse in Apollo. Again, that's a Genome Browser, and the plugin on top of it, not a database. Yeah. And then quickly, in the last 10 minutes, I am going to share with you just a very brief lay of the land for the National Center for Biotechnology Information Database. How many in here have used the NCBI website? Yeah, most of you. Exactly. So you're very familiar with this. NCBI does not only work with the whole genome data, it has a huge collection of information. You have, of course, you have variants, you have genes, proteins, you have population sets, you have bioprojects that define your sample, you have all sorts of data and all sorts of databases in here, and of course the bibliography database. So if you went to this is just the homepage for the NCBI, if you went to the homepage and clicked on the tab that says genome when you are trying to look for a database and enter the word Manakin, unlikeable, NCBI will actually just directly send you to Manakin Genomics. So if you're looking for Pipra, you have to go look for it a different way. I actually have to type in Pipra. A little bug of an over-aggressive search algorithm. But anyway, so on the left, on the left you have information from the golden color Manakin, just the general information. You have the list of the representative of the genome. You have the ability to go to the FTP site and get information as well from the GFF, your GFF files or your GFF file, like they still exist 25 years later. And you have also links to go to the collections of genes. There's a lot of information regarding the bioproject. When you were submitting these sequences, you had to provide all of this information. So this is information that's provided by us, the community. If I go to the gene database instead of the genome database, and I type the same name, then I'm going to find a gene of all 22,000 predicted gene models that the Genome pipeline constructed. When I say the Genome pipeline, I am referring to the series of steps of software that the NCBI Institute runs that combines all of those ab initio predictors and all of those that use the experimental data and build all of these gene models for us. It's very robust, it's very complex, and is not possible to replicate outside of NCBI. So it's a bit of a black box, but it's a very well described black box for those of us that are interested on figuring out how the gene models are constructed. So we trust that these data are actually reliable and useful. Not perfect, but a little bit better than me running the prediction software on my own machine as we experienced in the early stages. It was a bit more difficult. So you find the list of genes, or you can actually enter the name of a gene here, or if you have the identifier, you can enter the name of the identifier. And another way that you can get to one of the genes from the genome is by just interrogating our genes. So if you have a sequence already, if you're starting from the knowledge of having a chunk of a sequence, a protein, or you're having, or just nucleotide sequence, then you can go to the blast page of NCBI. I have lived here many years of my life. In this case, I've gone to the protein blast, and I have entered an amino acid sequence that I have for one of the genes of interest. And it's going to sound familiar to Mike, because it's one of my genes. And so I just gave it that name of beta-beta carotene from Vibra Filicata. And vast amount of results that you'll get from the BLAST database is going to give you an assortment of just hits, HTSs that are going to be coming from the searches. I'll skip that part. Again, that's one that I'll go very much in detail once we're doing our actual workshop. But this is what it will eventually take us to. You get a list of genes like the same list of genes that we have gotten before. Those are just two different ways to get to that. And then you can go and explore all of the data that is available for each of the genes already in NCBI. So in this case, for the beta-carotene oxygenase 2 from the Parana, you get information, just a little summary that tells you things about taxonomy, things about the type, and then you have this tiny little representation of the browser for this particular gene. You also get a browser within the browser, so the NCBI database provides their own browser. It's annoyingly reactive, so whenever you're clicking on it, it just like starts popping everything. But it gives you an idea of how this particular gene is laying on the region of the genome that we're inspecting. In this case, we can see, for instance, these are two different forms of the gene of interest, and one is missing an exon here. You see that? So there is already two different isoforms that have been identified here, and the same for this other gene model that you can actually explore these genes a little bit more in detail. I didn't do a screenshot of that, but if you hover over these different regions, then the database is going to show you additional information about them. There's also information about if a functional mutation has been done, then you'll find information about the gene ontology terms that are associated with this particular gene. You also have information about orthologs. In this case, down here at the bottom, in addition to the information about its location on the chromosome, you'll also find all of the sequences for all of the isoforms. On the left, you have the nucleotide, the mRNA sequence, and then on the right, you have the amino acid sequence. When you explore one of those records, this is just more information about the sequence as it lies on the chromosome. But when you explore one of those records, you cannot see it here, but let me assure you that there is information regarding the assembly, who provided the information for that sequence, publications that are associated with that particular reference, and then you also find information about how the coding sequence is laying down on the chromosome. This is important if you just want to get information about that particular gene. And then almost invisible here, this little tab says past state, because you're able to get information from this gene in this format as it is laid down on their standard gene page, or you can also just go and retrieve the FASTA sequence for your sequence of interest. These are the sequences that you're going to use in your analyses. These are the ones that you can use to interrogate other genomes. So this is all from PITA, but if I want to go and interrogate any of the other 4 genomes that are sequenced, I can use these in the instances that we have from JBROS, or the ones that are available. So for instance, Ensemble has the Manacus vitellinus genome, but it doesn't have PIPRA, so you can interrogate the one with the L that I don't remember what it's called, using these. And I think that is all I have from our tour of NCBI. So this is basically our aim with this is to offer you a summary of the different resources that are currently available that allow you to explore the genome on a much more detailed basis, right? Like nucleotide by nucleotide, gene model by gene model, and then the ability to export some of those sequences in the way that Ensemble is doing it through biomarks, in a way that we do it just very simply by either offering you the GFF3 or the nucleotides themselves, or in the way of what NCBI is doing. We're very fortunate that we actually have these genomes available on the international databases. And yeah, so I'm hoping that this is a good tool for you guys. Do you have any questions?